Okay, hello everybody, it's Math Martin, and if you're in my class, this is for my calculus students, and this is us going through one of the sections that you will need to read for homework. And if you're not in my class, welcome, and I hope you enjoy looking through some calculus stuff with us. We're going through the textbook that we use is Calculus of a Single Variable by Ron Larson and Bruce Edwards. Okay, so the section that we're on right now is we're about to start talking about continuity and one-sided limits. So basically what we're going to do is I'm going to go through and read this mainly for my students and explain some of the concepts, and it's kind of like just an audiobook read-along so that they'll know what they need to focus on while they're looking through the textbook. So I hope it helps, and see you all in class on Monday. So if we look at this, let's look at the AP tips first. Okay, so oh, by the way, if you don't know me, I love flamingos, so here's my nice little flamingo pointer to help follow along. All right, so it says you must know the precise definition of continuity for the multiple choice section, rarely the free response section, of the AP exam. Must be able to understand which condition of the definition is not met if a function is not continuous at a particular point. Okay, so this is very true. The continuity stuff shows up on the exam all the time, and you have to justify if you know that a function is continuous or not. And you really need to know the definition. So it's like one of those main definitions that I'm going to drill you on like all year long. So that's why they put that there. All right, so let's look at, these are just like what the goals are for this section. We're just going to jump down to this part. All right, so follow along in your book if you're my student. All right, so continuity at a point and on an open interval. In mathematics, the term continuous has much the same meaning as it has in everyday usage. Informally, to say that a function f is continuous at x equals c, so some random number for x, means that there is no interruption in the graph of f at c. So like basically you can draw it without having to pick up your pencil. That is, its graph is unbroken at c, and there are no holes, jumps, or gaps. Figure 1.25 identifies three values of x at which the graph of f is not continuous. At all other points in the interval a to b, the graph of f is uninterrupted and continuous. Okay, so let's look at these three different examples they've given us. So right here, we see that we've got f of c is not defined, so there's a hole right here. So we talked about that with limits. So the limit actually exists there because we talked about how the left side and the right side are coming to the same point, but it's not continuous because there's not an actual point here at this hole. On this one, we talked about how this is a jump discontinuity, so our graph goes up and like has a point defined here, but then it jumps down to finish the graph. So this also means the limit doesn't exist, right? Because the left and the right side aren't equaling. Okay, so it's also not continuous and there is no limit. And then over here, we've got another hole, but they actually defined it at a lower point. So, but the limit, so like the left side and the right side are saying that it should be up here, and the actual function value is down here, okay? So it's not continuous. The limit exists, there is a limit, but it's not continuous because the point's defined down here and the rest of the function's up here. You have a gap right here, okay? So it appears that the continuity at x equals c can be destroyed by any one of these three conditions. So one, the function does not define at x equals c, so that's this guy up here. There's just a hole. All right, two, the limit of f of x does not exist at x equals c. So if the limit doesn't exist, it's just not continuous at all. So this is like those jumps right here. And three, the limit of f of x exists at x equals c, but is not equal to f of c. So this is like the limit exists, like we have a hole, but the function says the y value should be like somewhere else. So if the function doesn't equal what your limit equals, then it's not continuous. This one throws people off the most, so we'll have to practice that a little bit more. But basically, you can still have a limit and not be continuous. All right, so let's look at the definition of continuity, which is down here at the bottom of our page. So continuity at a point. A function f is continuous at c when these three conditions are met. I would write this down in my notes if I were you and put a big star by it because this is super important. So it's a function is continuous if f of c is defined, so you actually have a point. The limit when you go to x equals c exists, and the limit and the function both equal each other. So basically 1 and 2 give you the same answers as what 3 is saying. So it's defined, the limit exists, and the limit and the function point actually equal the same thing. All right, continuity on an open interval A function is continuous on an open interval a to b when the function is continuous at each point in the interval. A function that is continuous on the entire real number lines from negative infinity to infinity is everywhere continuous. So basically, you can say that it's continuous like forever if it's never going to have any of these crazy occurrences. So most of the time, polynomial functions fit that definition, right? Because they don't have anything crazy going on. We'll see that. The exploration over here, you all don't have to worry about right now because we're going to do that in class together, just so you know. All right, let's look at our further reading right here. 1 second, let me move this over. Okay, so it says consider an open interval I that contains a real number c. If a function f is defined on I except possibly at c, so it's defined for the whole interval except maybe at c, if f is not continuous at c, then f is said to have a discontinuity at c, which we've used that word in class already a few times. Discontinuities fall into two categories, removable and non-removable. A discontinuity at c is called removable when f can be made continuous by appropriately defining or redefining f as c. For instance, the functions shown in figure 1.26a and c have removable discontinuities at c, and the function shown in 1.26b is non-removable. Okay, so let's look at these. We've talked about these in class a little bit. So having a whole or having a whole with a new defined point, those are called removable discontinuities, which we've seen when we've done like factoring with limits, and that you can still get a limit, like the limit still exists even though the point's not there. Okay, non-removable are like jumps. So like there's still no limit no matter what we do, and it's not continuous. Okay, so if there's just like a hole missing, that's a removable because we can factor out and still get an answer. There's still a limit. This one there is not. Okay, so let's look at example 1 together. Okay, discuss the continuity of each function. So A says f of x equals 1 over x. So the domain of f is all non-zero real numbers, because you can't divide by 0, right? So you can conclude that f is continuous at every x value in its domain. At x equals 0, f has a non-removable discontinuity, okay, which is actually shown down here. This is the graph of 1 over x. Okay, dividing by 0, see how we get this asymptote, the vertical asymptote, which we've talked about before, okay? So limit doesn't exist when you go to x equals 0 from either side because it's unbounded, okay? It's also not continuous there. In other words, there's no way to define f of 0 so to make the function continuous at 0. So it's continuous everywhere else, but it's not continuous at x equals 0 because it has a vertical asymptote. All right, let's look at this next one. So B says g of x equals x squared minus 1 over x minus 1. The domain of g is all real numbers except x equals 1. So if we plug in 1, that would be a problem because you'd be dividing by 0, but you'd also have 0 over 0, right? So you can conclude that g is continuous at every x value in its domain. At x equals 1, the function has a removable discontinuity. By defining g1 as 2, the redefined function is continuous for all real numbers. Okay, so if we look down here, there's a hole right here. So we already know that we can factor and do stuff to move around and still get a limit. So there is still a limit here. It's going to 2, even though the point doesn't exist right there. Okay, so that's kind of like similar to the limit problems we did this week. All right, part C, we got a piecewise function. So you have h of x equals x plus 1 for x is less than or equal to 0, and it equals x squared plus 1 if x is greater than 0. All right, the domain of h is all real numbers. The function h is continuous from negative infinity to 0 and from 0 to infinity, and because the limit of h of x as x goes to 0 equals 1, it's continuous on the entire real number line. So if we look down here at graph C, okay? So what they do when they graph piecewise functions, because I know this throws some of you all off. So for x is greater than 0, so we start here and go this way, you're just graphing the function x squared plus 1, so the parabola that starts at 1 on the y-axis. And then if it's less than or equal to 0, you're graphing the line x plus 1, hence the reason it goes straight right here. So what happens is we got to see if it's defined at 0. So if you plug in 0 for the top part, 0 plus 1 is 1, so it is defined, okay? The limit as you go from the left and from the right is saying that when you go to x equals 0, the y value should be 1, so that's good. So plugging in 0 and finding the limit at 0 gave you the same answer of 1, so therefore this whole thing is continuous. All right, and last one, D says y equals sine of x. Lovely trig functions. So the domain of y is all real numbers. You can conclude that the function is continuous on its entire domain, negative infinity to infinity, as shown here. So sine of x is like a lovely roller coaster going up and down, all right? And it doesn't have any crazy gaps or things where it's undefined. Sine of x is one of those continuous functions that you just need to memorize that it's always going to work. Now when we add other stuff with it, that's when it becomes a problem. But sine of x is defined for all of its points when it's just this. Okay, let's see what's next. Oh, and don't forget, if you're my student, you feel free to pause the video at any point if you need to catch up on writing notes or go back and look at something. All right, one-sided limits and continuity on a closed interval. So to understand continuity on a closed interval, you first need to look at a different type of limit called a one-sided limit, which we have already done, so good job, guys. For instance, the limit from the right, or right-hand limit means that x approaches c from values greater than c. This limit is denoted with like a little plus sign like we've been doing in class. Okay, so like what they say over here in the graph as you're approaching c from the right, so you're looking at the right side of the graph. Okay, the limit from the left, or left-hand limit, means that x approaches c from values less than c, and so it's denoted with a little negative or minus here to show you're going from the left side. So over here in this graph, we're approaching the limit from the left. Okay, one-sided limits are useful in taking limits of functions involving radicals. For instance, if n is an even integer, then the limit as you go to 0 from the right for the nth root of x equals 0 because you're taking the square root of 0 or the fourth root of 0, etc. All right, so let's look at the examples that they've given us. Find the limit of f of x equals the square root of 4 minus x squared as x approaches negative 2 from the right. Okay, so if we look at the graph here, okay, so you've got a half circle, and if you're going to negative 2 from the right, okay, it looks like we're going down to 0, all right? So if we look here, they said the same thing. If you approach negative 2 from the right, okay, then you end up getting, if you even plugged it in, then you get square root of 0, which equals 0. Okay, this is one of those where direct substitution solves it for you. One-sided limits can be used to investigate the behavior of step functions. One common type of step function is the greatest integer function, which is denoted like this. It's got like double brackets around x. Okay, so the greatest integer n such that n is less than or equal to x, which we're going to look at down here in this example in a second. This shows up very rarely on the exam. It's just like one of those random functions that's defined, but not really something you do a lot of work with. So, for example, the greatest integer for if you plugged in 2.5 would be 2. And the greatest integer for negative 2.5 would be negative 3. So let's look at the graph so it kind of makes more sense, especially for visual people. All right, so here is the graph of the greatest integer function. Okay, so if you were at 2.5, okay, so 2.5, like right here for your x value. If you go up to the graph, all of any x that's between 2 to 3, your answer is always going to be 2. Any x that's between 1 to 2, your answer is going to be 1. Okay, and they're like emptier holes at the end so that you're defined for the next step up. Okay, so if you're at negative 2.5, which doesn't show on this graph, but negative 2.5, you would jump down here and you would be at negative 3. Okay. All right, so find the limit of the greatest integer function as x approaches 0 from the left and from the right. So if you look here, if you're going from the left for going to 0, we're down here and our answer is negative 1. We're down on this negative 1 line. If you're up at the right, though, you're saying that y equals 0. So the limit doesn't exist at x equals 0 because the left side and the right side limits don't equal each other. So unless you're like in between integer values, this thing has lots of limits don't exist, obviously, because it's lots of jumps. Okay, the greatest integer function has a discontinuity at 0 because the left and right hand limits at 0 are different. By similar reasoning, you can see that the greatest integer function has a discontinuity at any integer n. So basically, it steps up. That's why it's called the step function. All right, let's look at the next thing. When the limit from the left is not equal to the limit from the right, the two-sided limit does not exist, which you all already know. The next theorem makes this more explicit, so it's basically just the definition of a limit. So let f be a function and let c and l be real numbers. The limit f of x as x approaches c is L if and only if, that's a biconditional from geometry, by the way. They get used in definitions all the time. So if the limit for x approaches c from the left of f of x equals L, and the limit as x approaches c from the right of f of x equals L. So this is basically what we talked in class already. The left side and the right side have to equal the same thing, then the whole limit exists. The concept of a one-sided limit allows you to extend the definition of continuity to closed intervals. Basically, a function is continuous on a closed interval when it is continuous in the interior of the interval, so everything like in between a and b, okay, and exhibits one-sided continuity at the endpoints. Okay, this is stated formally in the next definition. So a function f is continuous on the closed interval a to b, brackets because it's closed. You might want to write this down in your notes, just saying. When f is continuous on the open interval from a to b, okay, so we got this continuous function. The limit as x goes to a from the right equals whatever the point is for f of a, and the limit as x goes to b from the left equals what f of b is. Okay, so basically it's saying like we did earlier, the limit has to equal what the y value is. So if the limit is approaching the same point that they say like the graph is pointing at, then your limit exists, okay, and it's a continuous function. All right. Similar definitions can be made to cover continuity on intervals of the form like open to closed or closed to open, or those that are neither open nor closed or infinite intervals. So for example, square root of x. The graph square root of x like starts at 0 and then just kind of swoops over. It's continuous on the infinite interval from 0, close bracket of 0, to infinity. And the function g of x equals the square root of 2 minus x is also continuous on the infinite interval from negative infinity to 2. So basically, this is how they take care of those that like stop and don't keep going. As long as your limit as you approach the endpoint is the same as the y value that the endpoint says, then it's continuous. All right, so let's look at this example down here. Another half circle. All right, discuss the continuity of f of x equals the square root of 1 minus x squared. So they have our lovely graph over here. The domain of f is the closed interval from negative 1 to 1, closed brackets, okay? At all points in the open interval from negative 1 to 1, so everywhere on the line, it's continuous. And because as you approach from the negative 1 from the right, you're getting 0 and the point is at 0. And then if you approach from the left, same thing, the y value is 0 and the limit says it's going to 0. So therefore, this is continuous. All right. Let's see what's going on here. Okay, Charles' law and absolute 0. Okay, let me get this lined up a little bit here. Okay, the next example shows how a one-sided limit can be used to determine the value of an absolute 0 on the Kelvin scale. All right, so they say over here, by the way, Charles' law for gases, assuming constant pressure, can be stated as volume for V equals K, which is a constant, and then T is temperature. All right, on the Kelvin scale, absolute 0 is the temperature 0K. Although temperatures very close to 0K have been produced in laboratories, absolute 0 has never been attained. In fact, evidence suggests that absolute 0 cannot be attained. How did scientists determine that absolute 0 is the lower limit of the temperature of matter? What is absolute 0 on the Celsius scale? All right, so then they're walking through all this. Okay, so solution. The determination of absolute 0 stems from the work of the French physicist Jacques Charles. I'm assuming I said that right, hopefully, 1746 to 1823. Charles discovered that the volume of gas at a constant pressure increases linearly with the temperature of the gas. The table illustrates this relationship between volume and temperature, okay, volume and temperature. To generate the values in the table, 1 mole of hydrogen is held at a constant pressure of 1 atmosphere. The volume is approximated and is measured in liters, and the temperature, T, is measured in degrees Celsius. Okay, so all these temperatures are degrees Celsius, and then we got our constant pressure, our volume, which is measured in liters. Okay, the points represented by the table are shown in figure 1.33, so they graphed it for us, okay? Moreover, by using the points in the table, you can determine that T and V are related by the linear equation, so they gave us the linear equation that connects all of these together, okay? For solving for the temperature, you get an equation for the temperature of the gas, which they just solved for T from this guy. By reasoning that the volume of the gas can approach zero but can never equal or go below zero, you can determine that the least possible temperature is the limit as your volume goes to zero, okay? So they just did that. They tried to figure out what would happen if you plugged in zero for volume, okay? And then when they do these calculations, you get approximately negative 273.15. So absolute zero on the Kelvin scale is approximately negative 273.15 on the Celsius scale. Okay, and as you see down here, it goes down to about that value right here, and it's a linear function, so it's continuous. All right. The table below shows the temperature as an example 5 converted to Fahrenheit. Okay, nice. Try repeating the solution shown in example 5 using these temperatures and volumes. Use the result to find the value of absolute zero for the Fahrenheit scale. If you feel like doing that, go for it. But it's just showing you that they can plot it, and they found an equation to plot this, and then they use the fact of a limit, right-sided limit, to figure out what the value would be. All right. Let's go on. Okay. Properties of continuity. Okay, so these are like the same old properties that like show up all the time in math, and it's nice because it always works. All right, you studied several properties of limits back in 1.3, back a few weeks ago. Each of those properties yields a corresponding property pertaining to the continuity of a function. For instance, in this theorem, if b is a real number and f and g are continuous functions at x equals c, then the functions listed below are also continuous. So basically it's saying if you have a continuous function and you multiplied it by a number, so scaled it up, it's still continuous. And if you add or subtract two continuous functions, they're still continuous. And if you multiply them, they're still continuous. And if you divide them, they're still continuous as long as the denominator doesn't equal zero at c, which we all know. All right, so basically the same stuff that we always talk about. All right, it's important for you to be able to recognize functions that are continuous at every point in their domains. The list below summarizes the functions you have studied so far that are continuous at every point in their domain. So like always, polynomial functions, super helpful. They don't have anything crazy going on with them, and they're always defined, always continuous, they always have limits. So love those polynomials. Next is rational functions, as long as the denominator doesn't equal zero. So that worked out great. Radicals always work. And the trig functions, which they have some weird things going on with them at different parts, but they're continuous when they don't have anything crazy going on, like when you don't add stuff to them. All right. You can conclude that a wide variety of elementary functions are continuous at every point in their domains. All right, so let's talk about what's going on down here. So, by Theorem 1.11, it follows that each of the functions below is continuous at every point in its domain. All right, so they're saying this is continuous because x by itself is just a polynomial, and sine of x is continuous, so if you put them together, it has to be continuous because you can add or subtract continuous functions. Same thing here, this is just 3, so a scalar multiple multiplied by tangent of x, which is continuous, so this whole thing has to be. And when you're doing your rational functions with a polynomial and a trig function. Okay, all right, so they're called composite functions because they've got multiple things going on here. So like this one, sine of 3 of x, okay? So sine of x is the outside function and 3 of x is on the inside. Square root gives you your outside function. X squared plus 1 is your inside function. And then tangent's your outside function, and 1 over x is your inside function. So composition functions are when you have a function inside another function. So if g is continuous at c and f is continuous at g of c, then the composite function of f of g of x, or like this, how I like to write it, is continuous. So basically, if they're both continuous and they're continuous at c, the whole thing's continuous. All right, so let's talk about if these things are continuous or not, these examples. All right, so describe the intervals on which each function is continuous. Okay, so first one, tangent of x. The tangent function, f of x equals tangent of x, is undefined on this like pattern right here. So if we look at, let's look down here at the graph. So here's tangent. Okay, so if you notice it's got asymptotes going on here, okay? So it has an asymptote at pi over 2, okay? And then if you just repeat that and add like pi to it, okay? So it's like every pi over 2 in between your pi's, okay? So it's not defined there. It has vertical asymptotes. All right. So at all other points, though, it's continuous. So f of x equals tangent of x is continuous on the open intervals. So they've got like negative pi over 2 to pi over 2, pi over 2 to 3 pi over 2, and then it just keeps going. All right, next one. You have a piecewise function. So the top says it's sine of 1 over x when x is not equal to 0, and it just equals 0 when x equals 0. Okay, so let's look at what's going on there. Okay, 1 over x is continuous except at x equals 0, obviously, because you'd be dividing by 0. And the sine function is continuous everywhere. So it follows that this has to be continuous except at x equals 0. That would be a problem. So at x equals 0, the limit of g of x does not exist. Okay, so we'll look down here at this graph in a second. So g is continuous on the intervals from negative infinity to 0 and from 0 to infinity. So it's not continuous at 0. So if you look down here, this function is an example of oscillating. It's going kind of crazy here. All right, so it goes back and forth, and if we could zoom in on here, which, you know, feel free to graph this in your own graphing calculator, you'll be able to see like what's going on. Okay, but it's defined everywhere else. All of this is continuous, just going up and down, up and down. It just isn't defined at 0. All right, last one. H of x equals x times sine of 1 over x when x is not equal to 0, because they don't want to divide by 0, and then it equals 0 when x is 0. Okay, this function is very similar to the one we just did in part B, except that the oscillations are damped by the factor of x. So using the squeeze theorem, which we talked about last section, okay, so this function is in between, it's being squeezed in between the absolute value of x and the negative absolute value of x, okay, hence these like V shapes, okay. So basically, the function comes down and is like getting stuck in between these two. All right. So the limit as you go to 0, because of the squeeze theorem, you can assume that the limit as you go to 0 is 0 because the limit for the absolute value of x is 0, and the limit for the negative absolute value of x is 0. Okay. So it's defined on this one's continuous the whole time because the limit equals the y value, because they said when you plug in 0, you get 0. So this thing is actually defined as continuous the whole way. All right, there are some really specific random examples. All right, so let's talk about this theorem, which is really important, and it's one of our big star theorems. Okay, so the intermediate value theorem, which we're going to talk a little bit more in class, either this week or next week about. You can abbreviate it as IVT. It's one of the big 5-star theorems that I've told you all about in class, so you definitely need to write this down. It's an important theorem concerning the behavior of functions that are continuous on a closed interval. Okay, and like they said over here in the AP tips, you have to be able to apply it in the multiple choice and the free response. It's a big deal, okay? So if f is continuous on a closed interval, okay, so you're in between a and b brackets, f of a is not equal to f of b. So whatever the y value is at the left side is not equal to the y value on the right side. K is any number between those two. So k is any number between their y values. Okay, that's a key thing. F of a and f of b. So it's some y value in between. And there is at least one number c, so an x value, such that f of c equals k. So basically it's saying if you're continuous on a closed interval, there has to be at least one x somewhere that gives you the specific y value that's in between the two endpoints. It makes a little bit more sense when we look at it visually, which I'll show you in just a second. All right, the intermediate value theorem tells you that at least one number c exists, but it does not provide a method for finding c, so it just tells you it's there, it's possible. Such theorems are called existence theorems. By referring to a text on advanced calculus, you will find that a proof of this theorem is based on the property of real numbers called completeness. The intermediate value theorem states that for a continuous function f, if x takes on all values between a and b, then f of x must take on all values between f of a and f of b. All right, an example of the application of the intermediate value theorem, consider a person's height. A girl is 5 feet taller on her 13th birthday and 5 feet 7 inches tall on her 14th birthday. Then for any height between 5 feet and 5'7", there must have been a time somewhere where her height was exactly this random height in between there. This seems reasonable because human growth is continuous and a person's height does not abruptly change from one value to another. So basically it's saying as you grow up, you eventually had to hit all the heights between when you were little to where you are now, okay? The intermediate value theorem guarantees the existence of at least one number c in the closed interval where this exists, okay? There could be multiple times where you get the same y value. A function that is not continuous does not necessarily exhibit the intermediate value property. So for example, we're going to look at these graphs. Okay, so what they're saying, you're in between A and B. Here's f of A up here. Here's f of B down here. Okay, so two different y values. So what they're saying is, let's say we're looking for this y value k. Okay, so on this graph, there's actually 3 times that you hit that y value. Okay, you're guaranteed to have at least one, because if you're drawing a continuous line going from here to here, you're going to pass through k at least one point. All right, but you could do it multiple times. If it's not continuous, you have f of A up here and f of B down here. If it's not continuous, you're not guaranteed to pass through k, because you could do like this graph's doing and jump and completely skip it. Okay, so it's possible for non-continuous functions, but it's not guaranteed. All right, the intermediate value theorem often can be used to locate the zeros of a function that is continuous on a closed interval. Specifically, if f is continuous on A to B that's closed and f of A and f of B differ in sign, then the intermediate value theorem guarantees the existence of at least one zero. So basically they're saying if f of B was up here in the positives and f of A, and f of B was down here in the negatives, you're guaranteed that at least one point the graph crosses the x-axis, because it has to go from A all the way down here to B. Okay. And let's look at this application. So an application of the intermediate value theorem. Use the intermediate value theorem to show that the polynomial function f of x equals x cubed plus 2x minus 1 has a 0 in the interval 0 to 1. Okay, so we know it's continuous because it's a polynomial. And then they want us to just be in between 0, 1. So to find your endpoints, you would plug in 0 and get an answer, and you'd plug in 1 and get an answer. So if we plug in 0, we're at -1 for our y value. If we plug in 1, we're at 2. Okay, so they plot out the points 1, 2, and 0, -1. Okay, so you can apply the intermediate value theorem because we know it's continuous and f of A is not equal to f of B. Okay, so therefore there has to be at least some number where you're crossing the x-axis. So that means there has to be at least one x, some c, where y equals 0. Now again, it doesn't tell you how to find that, it just tells you that it exists, okay? So let's see what this is saying. The bisection method for approximating real zeros of a continuous function is similar to the method used in example 8. If you know that a 0 exists in the closed interval, then the 0 must lie in the interval like halfway, okay. From the side, you can determine which intervals contain the 0, okay, blah, blah, blah. That's just like a tip for how you can find zeros. But we've done that before. Zeros is basically like, you know, where you can do quadratic formula or you can factor and all that stuff. And since it's a polynomial, I know you can do that. All right, so we're going to dive into this whole section like this week and next week and talk about continuity and how it connects to limits. And then we're going to move on to learning about derivatives. Woohoo! All right, hope you all found this video helpful. And don't forget to write down those definitions and notes. And I will see you all in class. All right, bye.